Okay, so we now know how to test for autocorrelation using two different approaches. But what would be the consequences for ordinary least squares estimation if we were to have autocorrelation in the residuals of our estimated model, but we were to ignore that and carry on regardless? What would be the consequences for our coefficients and their standard errors? Well, it turns out that the consequences of autocorrelation in residuals are very similar to the consequences of heteroscedasticity. That is, the coefficient estimates derived using ordinary least squares are still unbiased and therefore consistent, but they are inefficient. In other words, they're no longer best linear unbiased estimators, or they no longer have minimum variance among the class of linear unbiased estimators. So the upshot of that is that our coefficient estimates will be okay, but our standard errors could be wrong. There therefore would exist the possibility that we could make the wrong inferences based on test statistics calculated using those wrong standard errors. Once again, whether the standard errors that we estimate using the usual ordinary least squares formulae are too small or too large will depend on the nature of the autocorrelation. That is, if we've got positive autocorrelation or negative autocorrelation. If, as is more likely in practice, we've got positive autocorrelation in the residuals, that would again lead the estimated standard errors on the coefficients to be too small for the slopes relative to the values that they should take in the presence of autocorrelation. A further consequence of autocorrelation is that R squared is likely to be inflated relative to its appropriate or correct value for positively autocorrelated residuals. One reason why that occurs is that positive residual autocorrelation leads to an artificial reduction in the residual variance, which leads to an artificial increase in R squared. So those are the consequences for our regression model and our ordinary least squares estimator if we've got autocorrelation in the model but we ignore it. Now, given those consequences, if we decide that those are serious enough to do something about the autocorrelation, what can we do? Well, as with heteroscedasticity, we've got a number of possible remedies that we could consider. First of all, again, as with heteroscedasticity, if the assumption of the autocorrelation is known, we could use a generalized least squares procedure. Now, generalized least squares procedures for correcting for autocorrelation, sometimes known as autocorrelation corrections, used to be very common in economics and in finance. And one such approach, which assumes a first-order autocorrelation for the residuals, is known as the Cochrane-Orcutt iterative procedure. Now, such procedures were very common in the past, but these are now considered to be old-fashioned approaches to correcting autocorrelation. One of the reasons why these approaches have gone out of favour in recent years is that a paper that was written by Hendry and Meisen in the 1970s suggested that the problem of autocorrelation was probably less serious than the problems that could occur if we inappropriately use these corrections. More specifically, application of these corrections assumes a particular functional form for the model. More specifically, using the Cochrane-Orcutt iterative procedure validly assumes a set of what we call common factor restrictions are present in our model. Now, typically, if we tested for these common factor restrictions, we'd usually find that these were not present, and therefore that the autocorrelation correction, such as Cochrane-Orcutt, is not valid. So that being the case, using a generalized least squares procedure is somewhat risky. A more modern, in inverted commas, approach to a problem of autocorrelation in the residuals of an estimated model is to say that, in fact, autocorrelation presents an opportunity rather than a problem. And it presents an opportunity because it allows us to modify the regression model in a way that makes it better. Now, to see why that's the case, one thing we can write is we can write the dependent variable y that we're trying to explain as a function of the part of y which we do explain using the model, y hat, and a residual part. So we could write yt equals y hat t plus u hat t. Now, if the residuals from the estimated model are autocorrelated, that must mean there was some structure in our original dependent variable y which was not being captured in the fitted values of the regression model. So if there's autocorrelation in the series y, that's not being captured by the explanatory variables that we've used, by definition, if something is here and it's not modelled in here, it must end up in here in the residuals. So patterns in the residuals, like positive or negative autocorrelation, are indicative that there was a richer structure in our original explanatory variable y than we are currently capturing in the model. What does that mean? Well, that means that we've got the opportunity to improve upon our regression model, to get a regression model that better explains the data by finding one that actually captures these features as well as the ones that we've already explained. So how can we actually do that? Well, all of the models that we've used so far have been entirely static in nature. We could say that the models have assumed a contemporaneous relationship between the dependent variable y and the explanatory variables, the x's. That is, what we've assumed is that if x2 changes at time t, that causes an instantaneous and immediate change in the same period of the variable y. So x2 changes in period t means that y changes in period t. It's very unlikely in practice, however, that a change in an explanatory variable x2 will lead to an immediate corresponding change in the explained variable y. The way that we get around that is to switch from a static model of this kind to what we call a dynamic model. Now, a dynamic model would be one where our current value of the dependent variable y is explained by reference to a set of explanatory variables x, but also a set of lagged values. Now, those lagged values could be lags of the explanatory variables, the x's, or they could be lagged values of the variable that we're trying to explain y. So we can add as extra regressors in our model the lagged values of x's, x2t minus 1, x3t minus 1, and so on up to xk t minus 1, and the lagged value of y, yt minus 1. Now, you can probably see already that once we move from a static model where every variable is present in that model in its current or contemporaneous form, when we move away from that to a dynamic model, we could also add more lags of the variables into the model. So, for example, we could add a 2-period lag of the variable x2, x2t minus 1. We could add a 3-period lag of the variable x3, x3t minus 3, and so on. We could add a 4-period lag of the variable that we're trying to explain y, yt minus 4. We could add as many lagged values of as many variables as we wanted to into this regression model. Now, an obvious question then is to say, well, how do we decide how many lags and of which variables should be included in a dynamic regression model? Well, there are two answers to that question, and unfortunately, again, there's no unique scientific answer. We can say as well that forming dynamic regression models is more of an art than a science. That is, there's no perfect, unique model that is the best one. All we've got is a number of competing ways to represent the data, all of which might have their merits. So the two approaches, and they're both slightly ad hoc, that we could use to determine the number of lags to add into the model are as follows. The first of these would be to revert back to financial or economic theory and to say we'll use that number of lags of the explanatory or explained variable that financial or economic theory suggests should be present in the model. So, for example, if financial theory suggests that adjustment of y to changes in x should occur within one period, then we would only use lags of time t minus 1 in the regression model and no further lags. It may be that financial theory says that it wouldn't make any sense for the current value of y to depend upon its previous values. So in that case, obviously, we would not include lagged values of y in the regression model, and so on and so on. The other and second approach to deciding how many lags we should include in the regression model would be to say, well, what we're trying to do by adding lagged values of the variables into the regression model is to ensure that the residuals from that estimated dynamic model are now free from autocorrelation. So we could use the decision rule. We'll add lags into the regression model until we have soaked up all of the autocorrelation in the residuals. So we could say, I will include in the regression model that minimum number of lags of the variables that are required to ensure that the residuals are free from autocorrelation. Obviously, if we included more lags in the model than the minimum number required to ensure that the residuals are free from autocorrelation, the residuals would still be free from autocorrelation, but those extra lags wouldn't be necessary to achieve that statistical objective. So, to summarise, we could decide how many lags to include in the regression model, either using a kind of financial or economic theoretical approach, or by using a statistical approach. And in practice, perhaps a combination of the two are actually often used together. So why might we actually want or need to use a dynamic model rather than a static one? In other words, why might we want or need to include lags of variables in a regression model? Well, there are broadly three reasons for including lags, and if any of these three things occurs, then in all three of these cases, in some senses, a problem of autocorrelation in a static model would be cured, in inverted commas, by switching to a dynamic model that included lags. The first and most common of these is if there's inertia of the dependent variable. So if there's positive autocorrelation in the residuals, this could result from inertia or slow adjustment of the dependent variable to changes in the explanatory variables. So for example, suppose that I was trying to model some variable y, which was monthly stock returns, let's say, using a set of explanatory variables which included the variable x2, and let's suppose that x2 were interest rates. Now, is it necessarily going to be the case that stock returns adjust immediately to a change in interest rates? Well, in this context, we could argue that we'd expect adjustment in stock returns to be relatively quick. People can adjust their positions in stocks fairly quickly. The market's very, very liquid. One share in a given company is exactly identical to some other share in a given company, and so on. But what if the variable that I was trying to explain, y, should put a T subscript in here, were, for example, house prices? Now, houses, on the other hand, unlike stocks, are relatively illiquid assets. If we try to sell a house, it's likely to take a long time. If I want to move into a bigger house, it's likely to take me a long time to find another house to buy, and so on. And every house has a certain degree of uniqueness about it. Houses are very heterogeneous. Therefore, if the Chancellor of the Exchequer in the UK increased the base rate of interest today, it's unlikely to have an impact on house prices today, because people can't do anything about their current housing position immediately in response to an increase in interest rates. So if interest rates go up today or this month, house prices may stop increasing as much, or they may fall, but that's unlikely to happen quickly. House prices may start to not increase so quickly this month, and they may fall slightly next month and fall more the month after, and so on and so on. So if our explanatory variable interest rates changes, the dependent variable y is likely to change only slowly or with a lag in response to that. We could call that inertia of the dependent variable, or slow adjustment, or we could call it underreaction of the variable y to changes in interest rates. interest rates change now, house prices don't change necessarily in this period, they change in the period after that and the period after that and so on. Also in finance, exactly the opposite phenomenon has often been found to occur, and that is, in many examples in finance, we found evidence of market overreaction. So for example, suppose a company announces a profits warning, or that the value of its dividend payment is going to be reduced compared to the value of the dividend it paid last time around. That's obviously a piece of bad news about the company and suggests that the company is doing relatively badly. That would lead share prices in that company, everything else being equal, to fall. But it's often the case that share prices fall by too much compared with how bad the news actually is, or how bad it isn't. So often what will happen is, if the share price starts off here, then the company makes an announcement that the value of its dividend is going to be cut. Maybe the share price falls down to here, but then the markets kind of take time to assess this information and decide, well, maybe things are not as bad as all that after all, so then the share price subsequently goes back up to here. So obviously this was the original level of share prices. This is the new appropriate level of share prices, given that the company now would be perceived by the markets and by the world as not being so strong as it was before this announcement was made. But between those two, we've got a fall in share prices that was greater than the amount required given how bad this news is. If this happened a number of times, and we didn't capture it in our model, this would lead us to have negative serial correlation or negative autocorrelation in the residuals. So inertia of the dependent variable, or underreactions or slow reactions, cause positive autocorrelation in the residuals of an estimated model. Overreactions of this type lead to negative autocorrelation in the residuals of an estimated model. In both of those situations, if we added lagged values of explanatory variables that were relevant into the model, or lagged values of y, if we added enough of them, we'd probably end up with a set of residuals from that dynamic model that was free from autocorrelation. A further circumstance where autocorrelation can arise in the residuals of an estimated model is if the dependent variable were a time series that was measured as a kind of overlapping moving average. If we have a set of overlapping moving averages so that the moving averages are constructed in an overlapping way, then if we estimate a regression model using that, a static one, we would usually end up with positively autocorrelated residuals because of the way that we constructed and used the data. However, there are several problems with regression models that can cause autocorrelation, either positive or negative, but which would not be cured necessarily by adding lagged values of the variables into the regression model. In other words, there can be some circumstances where we have autocorrelation, but adding lags of the variables would not be the appropriate response. So for example, if we omitted a relevant variable which was itself autocorrelated, what does that mean? Well, suppose that we estimated a simple regression model of yt regressed on a constant and a variable x2t. Okay, but let's suppose there was some other variable, x3t, which is an important determinant of y, but which we left out of the model. If x3t is itself autocorrelated, in other words, if x3t is related to its previous values and we've omitted it from the regression model, the estimated residuals u hat t that we get from this regression model that excludes the autocorrelated variable will be themselves autocorrelated. Now you can see that if we tried to cure autocorrelation in these residuals by adding lagged values of x2 into this regression model, that's not going to work. Because the reason that the autocorrelation is present there in the first place is that there's this other variable x3 that influences y, but which we left out of the model. So the appropriate cure for the autocorrelation in that circumstance would be to include the variable x3 that we'd omitted from our regression model. The second reason why we might find autocorrelation, but that autocorrelation would not be fixed by including lags of the variables in the regression model, is if we've committed what's called a misspecification error by using an inappropriate functional form. So for example, suppose that we estimate a simple linear regression model like this, but in practice the real relationship between y and x2 was a nonlinear one. So we've assumed a simple linear functional form for the regression model, but the true relationship between y and x2 is a nonlinear one. If that is the case, then sometimes we can end up with residuals from the linear model that we estimate being autocorrelated. And again, we couldn't cure that residual autocorrelation by adding lags of the explanatory variable into the regression model. The final cause of autocorrelation, which we haven't already spoken about and which probably wouldn't be cured by adding lagged values of the explanatory variables unless we included many of them, would be what we might call autocorrelation resulting from unparameterized seasonality. What's unparameterized seasonality? Well, we're going to discuss in much greater detail later in the course what seasonality is and how we model it in econometrics. But for now, seasonality is a phenomenon where something happens to our dependent variable periodically through time. So for example, stock prices seem to have a tendency to always fall in the autumn around October. And all seem to have a tendency, everything else being equal, to rise in January. If we were to look at the macroeconomy, we often find that, for example, consumer sales have a tendency to always rise just before Christmas time, that is in November and early December. If we estimated a regression model for stock returns, a monthly model, or we estimated a monthly model for consumer sales, then we may find that the residuals from those models were autocorrelated, and that autocorrelation would result from the seasonal patterns that were in that data that we hadn't captured. Now, we could capture those seasonal patterns using lagged values of the variables, but if we were using monthly data, we'd have to have 12 lags of the variables in order to capture what was happening through the year. So, for example, what we'd find in consumer sales is that consumer sales always peaked every December. So if we added 12 lags of the variables in, then that would capture the impact of that. But as we'll see later in the course, there's a much simpler way to allow for these seasonalities than using lags. So to summarise, we can cure, in inverted commas, a problem of autocorrelation in the residuals from an estimated model by switching from a static model, where all of the variables are measured contemporaneously, to a dynamic model which includes lags of the variables. In many cases, this will work to cure the autocorrelation, but there are a small number of cases where, because of the cause of the autocorrelation, adding lagged values simply won't do it. We have to do something else. Another approach that we can use to the problem of autocorrelation is to use a model in first differences instead of a model in levels. So for example, suppose our original model had been y equals beta 1 plus beta 2 x2t plus beta 3 x3t plus ut. What we could do, instead of estimating a model like this, where the level of y is said to depend on the levels of some explanatory variable x, we can instead move to a model for first differences. So then we would be saying that the change in yt depends on the change in x2t and so on and so on. And often it's the case that if y has autocorrelation, which appears in the residuals of an estimated model in levels, if we switch to a model in first differences, the residuals from the model in first differences are free from autocorrelation. Because the process of taking first differences, that is calculating yt minus 1, will in some senses remove the autocorrelation from the series at source. So our model then would be a regression of delta yt on a constant, delta x2t, delta x3t, and so on up to delta kt. Of course, Once we move away from a completely static model where we have only contemporaneous values of all of the variables in the equation to a dynamic model, that dynamic model could be extended in any number of different directions. So, for example, we could have a model where the dependent variable is the change or first difference of yt, and where some of the explanatory variables are in change form, for example, delta x2t, delta x3t, and so on. But also, we could have some variables which are in lagged levels forms in that expression. So, for example, delta yt could also depend on lagged values of x2, lagged values of x3, and lagged values of y itself. Notice that if the dependent variable for the regression model is the change in y between time t minus 1 and time t, then it only makes sense to include lags of the levels of the series as explanatory variables rather than the levels of the series in contemporaneous form. So if the dependent variable is delta yt, it wouldn't make sense to have x2t or x3t in levels forms on the right-hand side. Why is that the case? Well, the answer is that is the case because delta yt is the change in y from time t minus 1 to time t. Obviously, y can't change between time t minus 1 and t in response to a value that x takes only at the end of that period, i.e. at time t. So it only makes sense to have lagged values of the explanatory variables or of y in their levels form on the right-hand side of that expression and not contemporaneous values of the levels of those variables. Obviously, when we move from regression where we have a static model where the current value of y depends only upon current values of x, the model will obviously become much more difficult to interpret than it was previously. So we may have started off with a nice simple econometric model which tested some financial theory that we were interested in, but when we move to a model in first differences that might also include lagged values of the dependent or independent variables, the model is much more difficult to interpret than it was before. One property of the model which we can always calculate and which is always of interest to us in the context of dynamic models is what we call the long-run static solution to the model or the long-run equilibrium solution to the model. The idea essentially of calculating the long-run or static equilibrium solution to the model is that we determine what will be the long-run or underlying relationship between the explanatory and explained variables. So the definition of equilibrium that we use in econometrics is that equilibrium is reached when the values of all of the variables are no longer changing. So we could say yt equals yt minus 1, yt plus 1 equals yt plus 2 and so on. So in other words, at some kind of mythical point in the future, the values of all of the variables have stopped changing. Therefore, we don't need to use any time subscripts anymore. Similarly, xt equals xt plus 1 equals xt plus 2 equals x. So the values of all of the explained and explanatory variables have reached some steady state where they're no longer changing. One implication of that, of course, is that the first differences of all of these variables must be 0 by definition. Because if yt equals yt plus 1, the value of y isn't changing anymore, so delta yt is obviously going to be 0 in long-run equilibrium. So the way that we calculate the long-run static or equilibrium solution to a model is to conduct the four steps that I list on the overhead slide. And it doesn't matter what order we perform these steps in, we can do them in any order and we'll always get the same result. So we remove all the time subscripts from the variables because the variables are no longer changing. We set the error or disturbance term equal to its expected or equilibrium value of 0. We remove all first difference terms completely because obviously those are all 0 by construction. Finally, what we want is an expression where y is the subject of the formula and we've got explanatory variables gathered together on the right-hand side. So we take all the terms in y over to the left-hand side of the expression and all the terms in the explanatory variables we gather together and put on the right-hand side of that expression. To give you an example of how we calculate the long-run static equilibrium solution, let's suppose our dynamic model was delta yt equals beta 1 plus beta 2 delta x2t plus beta 3 x2t minus 1 plus beta 4 yt minus 1 plus ut. How do we calculate the long-run or static equilibrium solution for that model? Well, we do it by conducting the 4 steps that I've just spoken about. So first of all, we set the first difference terms all to 0 in the model. So delta yt equals 0, delta x2t equals 0, and so on. Secondly, we set the disturbance term equal to its expected value of 0. Then we get expression 0 equals beta 1 plus beta 3 x2t minus 1 plus beta 4 yt minus 1. Then the next step is to make y the subject of the expression, so we take y over to the left-hand side and all of the x's are left on the right-hand side. Then the final 2 steps are first of all to remove the time subscripts from all of the variables, so yt minus 1 becomes y, x2t minus 1 becomes x2, and we divide all through the resulting expression by beta 4. So we end up with the long-run equilibrium solution to that model being y equals minus beta 1 divided by beta 4. That would be their kind of intercept in long-run equilibrium, and minus beta 3 divided by beta 4 x2. And minus beta 3 divided by beta 4 would be the kind of long-run slope relationship between x2 and y. So the long-run static equilibrium solution is very useful. It tells us if we change the value of x2 by 1 unit, what will be the final resulting eventual equilibrium impact on y? And the static equilibrium solution will tell us that. So the static equilibrium solution is very easy to calculate. If we look at the static equilibrium solution for this particular model, we'll notice that it doesn't involve at all the coefficient beta 2. And the reason for that is that beta 2 is a coefficient attached to delta x2t. And as I said, in long-run equilibrium, all of the first difference terms will be 0, so delta x2t equals 0. We could think of all of the parameters attached to the first difference terms, for example, beta 2 in that expression, as representing the short-run relationship between x and y. Whereas beta 3 and beta 4 are the parameters that represent the long-run relationship between x2 and y. So that's how we interpret the long-run static equilibrium solution to a model. As with many things in econometrics, if we cure one problem, we often end up causing other problems as a result of that. And there are several problems associated with using a dynamic model that is including lagged values of variables in a regression model to cure autocorrelation. The first of these problems is that including lagged values of the dependent variable in the regression model violates the assumption that the right-hand side variables are non-stochastic or fixed in repeated samples. Notice that this assumption is not violated if we include lags of the explanatory variables. It's only lags of the dependent or explained variable that will cause this assumption to be violated. To see why this assumption is violated, consider the following. If this was our original regression model, I could take this model and lag it by 1 period. That is, I could subtract 1 from all of the time subscripts. The equation would then be yt minus 1 equals beta 1 plus beta 2 x2t minus 1 plus beta 3 x3t minus 1 plus ut minus 1. So now, when I've lagged this expression 1 period, we can see that the dependent variable is yt minus 1. Yt minus 1 is obviously a stochastic variable because the value of yt minus 1 depends partly on this disturbance term ut minus 1. So that being the case, if yt minus 1 is a stochastic variable in this equation here, if we add a lagged value of y, i.e. we add yt minus 1 into our original expression up here, so this becomes, for example, beta 4 yt minus 1 plus ut, then obviously if yt minus 1 is a stochastic variable here, it must also be stochastic when we include it in here. So we violated the assumption that all of the explanatory variables in here are non-stochastic or fixed in repeated samples. Does that matter? Well, the answer is asymptotically, or as the sample size tends to infinity, the problem that's created by violating that assumption in this way disappears. So as the sample size gets larger and larger, the impact of including this stochastic regressor in the regression model gradually disappears. However, for relatively small samples, we end up with biased, but obviously still consistent, coefficient estimates. So including the lagged values of the dependent variable in a regression model can lead to biased, but still consistent coefficient estimates. The second, and arguably the most fundamental problem with switching to a dynamic model to cure autocorrelation is that we may have cured a statistical problem, that is the problem of autocorrelation in residuals, at the expense of an interpretational or financial problem. That is, we may have had some idea from theory that our regression model related the current value of some dependent variable y to the current values of some explanatory variables, the x's. And we'll know, if we estimate that model, how we can interpret the values of the parameter estimates that we get from that model. But if we then switch to a model where the dependent variable is the change in y, and we've got changes in explanatory variables on the right-hand side, and we've got lags of the levels of explanatory variables and lags of y on the right-hand side, it becomes very difficult to interpret that equation. Obviously, we can calculate the long-run solution to that equation, but again, that might not be exactly what we wanted to do in the first place. So we may end up with this a model, a dynamic model that is, that's statistically perfectly well specified, but in terms of testing the financial theory that we started with, it simply doesn't. So we may end up with a perfectly well specified but practically useless model. And that's a very important problem in econometrics, and more generally, we often face trade-offs in econometrics between, on the one hand, having a model that's very well specified statistically, and on the other hand, having a nice model that tests the theory that we want to test and is intuitively easily interpreted. Finally, if there is still autocorrelation in the residuals of a regression model including lags of the variables, then the ordinary least squares estimator will not even be consistent. So if we add lagged values of variables into a regression model in an attempt to cure autocorrelation, but the residuals from this dynamic model are still autocorrelated, in other words, we haven't succeeded in removing all of the autocorrelation, then the ordinary least squares estimator won't even be consistent. That means even asymptotically, even if we had an infinite amount of data, we still couldn't be sure that we get the appropriate parameter estimates using ordinary least squares. So that's a very serious problem, and that suggests that if we try to cure autocorrelation using lagged values in the model, we better make sure we actually succeed in doing that. Otherwise, we'll have very serious problems potentially.